Yeah. So we have just recently seen that the interaction between the electrons and the phonons may be the source of the, say, collisions that have been discussed up to now during these lessons. And one thing we may do now is to see what is the effect of this kind of interaction over the resistivity of the system. So in this picture, if the resistivity is due to the interaction between the electrons and the phonons, then the resistivity will depend on the number of phonons that we have in the system and on the features of those phonons. But just by explaining what by the features of those phonons means I just rewrite the laws concerning the crystal momentum conservation. So this means that the crystal momentum of the electron after the interaction is equal to the crystal momentum of the electron before the interaction takes place, plus or minus, and we have the plus in case there is the absorption of a phonon, or the minus in case we have the emission of the phonon, h bar q, and q is the contribution coming from the phonon, plus an additional g in case we need that to balance the equation. And the second part is the energy conservation. So the energy of the electron after the interaction is equal to the energy of the electron before the interaction takes place, plus or minus the energy of the phonon, plus for absorption or minus for emission. We have just seen that in this case the energy of the electron after the interaction is nearly equal to the energy of the electron before the interaction, due to the fact that h bar omega s is very low. So in this case, if we remember this diagram concerning the dispersion of the frequencies, or also energies in this case, this is in the range of tens of millieV. So at this point, let's say we suppose that the final energy of the electron is nearly equal to the initial one. The main change is observed in this equation due to the fact that, again, the k values and q values for electrons and phonons are defined in the same volume. So due to that, let's say the main change that the phonon induces on the electron is on the wave vector, not on the energy. So if we just use the Fermi sphere to represent the electron states, what we have is that if we start with k, the final state of the electron will be always very close to the Fermi surface for what concerns the energy, and will have, let's say, a new value k prime of a new value of the wave vector k prime, and the distance between K prime and K depends on Q. So depending on Q, so depending on the wave vector of the phonon that interacts on the electron, the final state will be close or far away from the initial state. As we have done for the let's say evaluation of the specific heat, in particular in the low temperature and high temperature regimes, I will do exactly the same. I will use exactly the same approach now. So I will try to see what happens in the high temperature regime. So when T is large, or on the, let's say, on the phonon scale, the thermal energy is up here. So high temperature means that the thermal energy is up here, higher with respect to the typical phonon energies, and low T will be, again, the situation where the thermal energy is lower and lower with respect to the maximum phonon energy. So high T and low T always regards phonons, not electrons, because for electrons, we are always at low temperature, because due to their typical energies, in the solid state, we always, let's say, observe the electrons in a situation that is very close to the low temperature regime for the electron themselves. So what happens in the high temperature situation? Considering again the fact that the resistivity depends on the number of phonons. We will see later that there are additional degrees of freedom in this picture, but for the moment, let's concentrate on the fact that the resistivity is proportional to the number of phonons that we have activated that are active in the system. So in the high temperature regime, so when the temperature of the system is up here, then we expect that all the possible phonon states are active, because the thermal energy is larger with respect to the typical phonon energy for any arbitrary wave vector. So we expect again that all the phonons are active. In this picture, if we want to know what is the number of phonons that we have in the system, we may use to estimate that the Bose-Einstein distribution function. So the, let's say, number of phonons that correspond to a specific wave vector Q or polarization S is given by 1 divided by the exponential of h bar omega s of Q divided by kBT minus 1. So using the Bose-Einstein distribution function. This, in the high temperature regime, we may use a similar approximation. We may use an approximation that is similar to one that we use in the high temperature regime in the evaluation of the specific heat. In that case, if kBT is larger than h bar omega s of Q, then we may approximate this exponential with 1 plus h bar omega s of Q divided by kBT minus 1. So we may suppress simplify minus 1 and plus 1. So this is equal to kBT divided by h bar omega s of Q. So this means that the number of phonons that are active in the system is proportional to T. So, and this is valid irrespective of the value of the energy that you have here. So the energy is just a coefficient, because in this case, we're supposed to work at the fixed value of Q and just let T change depending on the temperature of the system. So in this case, what we have is that the number of phonons is proportional to T. if the number of phonons for any fixed Q and S parameters is proportional to T, then you expect the number of phonons is always proportional to T in the high temperature regime. So that's why you expect that in the plot of resistivity as a function of temperature, that's why you expect to have a linear dependence of the resistivity as a function of the temperature. So that depends on the fact that, again, the number of phonons is linear in the temperature. So the point is now to observe what happens when we suppose to work in the low temperature regime. So at that point, we may again consider the so the Fermi sphere. We are in the low temperature regime. In this picture, okay, so in this picture, in the low temperature regime, the energy of the phonons is low, lower than maximum value that you have here close to the border of the zone. So due to that, also the value of the energy, both the value of the energy and the value of the wave vector that may be associated to one of those phonons are low. So if this is the value of the wave vector for the starting level of the electron, then the final level of the electron will be close to the initial one. So if this energy represents kBT, the thermal energy, then you observe that thanks to the fact that here the energy versus wave vector dependence is linear, if kBT is low, also the corresponding maximum value of Q is low and proportional to T. So the important point is that in the low temperature regime, the maximum Q modulus, or in general the modulus of the wave vector of the maximum, the volume of the value of the maximum wave vector that you may observe in the phonon system is proportional to T, because we have again this linear dependence between energy and wave vector. So the smaller the value of the temperature, the lower will be the wave vector corresponding to a possible excited phonon corresponding to this maximum value for the phonon energy. So in this case, Q is proportional to T. So this deviation here that is given by Q is proportional to T. And let's say if we fix the value of Q, then the final state for the electron may be on this side, but may also be on this side. So if we fix the Q modulus, then the all possible states that may be accessed is found within this cone. So we have a cone where all the possible final states concerning the the electrons can be found in the system, and the let's say radius of that cone, so the cone radius is proportional to q, but we know that q is proportional to t, so the cone radius is proportional to t. If the if the radius of the cone is proportional to t, that means that the area of the cone is proportional to t squared. So t squared is the area of a cone, and the area of the cone represents the possible final states for the interaction. So in this case, we have that the possible final states, the number of possible final states, that means the number of possible phonons that may be accessed by the electron through this kind of interaction, is proportional to t squared. So the before, in the high temperature regime, we had not this problem, because in the high temperature limit, all the phonons are excited. So the, let's say, the equivalent of the area of the cone that we have in this situation does not depend on the temperature. So in that case, the equivalent of that was a temperature independent term. The only term that was depending on temperature was the number of electrons. So in that case, we need not to consider, we didn't need to consider the this dependence regarding the this effect, the contribution of this effect on the resistivity dependence on temperature. Then in this situation, we have to consider also other two effects that contribute to the resistivity dependence on temperature. One effect is the following. Before, let's say, during the first part of the lesson, we evaluated the coupling constant and in that case, what we observed that in the low Q limit, the coupling constant is proportional to Q to the power of 1/2. So the coupling, what is known is that the scattering rate is proportional to the square of the coupling constant. And if the coupling constant is Q to the power of 1/2, then the scatter rate is proportional to Q. So, and as we are in the low temperature limit, Q is proportional to T. So the contribution coming from the area of the cone, that means the contribution coming from the number of final states, is proportional to T to the power of 2. The contribution of the scattering rate is proportional to T. So we have T squared here times T. So we have T to the power of 3, considering this contribution and that contribution. But we need to consider also another term here when evaluating the dependence of the resistivity on temperature in the low temperature limit. Because if we suppose to, let's say, the change in velocity of the electron after the interaction depends on the fact that the velocity is related to the gradient of the energy. So if we change the point over the Fermi sphere where we evaluate this gradient, different points correspond to different orientations. But when the Q value is, the modulus of Q is very small, so when this cone, the area of this cone is very small, then the initial and the final velocities will be nearly equal, not just in modulus, but also in direction. So the point is that if Q modulus, or also if just Q is close to 0, then the scattering process is not very effective in changing the speed direction. So at this point, we may say that if q is very low, the initial direction of the speed of the electron and the speed of the final velocity of the electrons are nearly the same. So the capability of this process to induce a collision that has an effect that contributes to the modification of the direction of the speed of the electron decreases as the q value decreases. So to evaluate this contribution in general, let's say the parameter that is used is this angle. So the angle between the initial state of the initial wave vector of the electron and the final value of the wave vector of the electron, because theta in the low q limit, so q represents the deviation of k prime with respect to k. In the low q limit, I just make an expansion here. So if this is k, this is the surface of the sphere, and this is k prime. Q represents a straight vector that joins k to k prime. In principle, this angle, the angle is defined as the length of this part of the circle divided by the radius of the circle. But if this angle is very small, we may, let's say, suppose that the length of this part of the circle and the length of this straight line here are nearly the same. So for low q values, theta is nearly equal to q. So the value of theta is proportional to the value of q, not equal, because that is an angle and that is a wave vector. So we may say that the value of theta is proportional scales with the value of q. In general, the coefficient that is used to estimate how effective the scattering process is in changing the velocity of the electron is a coefficient that is 1 minus cosine of theta. So if theta is equal to 0, then 1 minus 1 is 0, so the process is not effective in changing the direction of the velocity. If theta is larger than 0, then at this point, 1 minus cos theta will not be 0 and will be, say, positive and non-zero. So at this point, we have again that the contribution of the process in changing the velocity increases as theta increases. In the low q limit, so that also means in the low theta limit, this is, we may expand the cosine of theta as 1 minus theta squared divided by 2. So this is theta squared divided by 2. So let's say the effectivity of the process is proportional to theta squared divided by 2. As theta is proportional to q, this is proportional to q squared, and as q is proportional to T at low temperature, it is proportional to T squared. So In summary, we need to consider three contributions regarding the resistivity, the behavior, the dependence of the resistivity on the temperature in the low temperature limit. One is due to the geometry, so we have to consider the area of the cone, the number of possible final states that contribute to this process. We have to consider the contribution of the scattering rate and the contribution of the fact that for fixed value of Q, as Q is reduced, the capability of this process to interfere with the original motion of the electron decreases due to the fact that the direction of the velocity of the electron doesn't change that much if the value of the exchanged Q is nearly zero. So if we now sum up the three contributions, so the final result so the final result is that when considering the resistivity dependence on temperature, we have T squared due to the geometry or the number of possible final states. Then we have a T term that is the scattering cross-section, and T squared, that is the efficiency of the process. So we have a T to the 5 dependence So here we have a T to the 5, and here we have a T dependence, so high temperature limit and low temperature limit. And again, we didn't consider all these features in the high temperature limit due to the fact that let's say, concerning the number of final states, let's say the area of the cone in the high temperature limit, the area of the cone didn't change as a function of temperature due to the fact that all the phonons are for sure acting in the system, so the temperature has no effect on the wave vector of the phonon, just on the number of phonons, not on the not on the geometry. So in that case, just on the number of phonons, not on the geometry on the scattering. So this term, the cone contribution needed not to be included, but just the fact that the number of phonons changed according to temperature. Then also here we consider the contribution of the scattering process due to the fact, not just due to the fact that there is no contribution of the scattering cross-section at high temperature, because let's say also in that case you have to consider the contribution of the scattering cross-section, but that again, since there are no constraints on Q, at that point the temperature is not effective in modifying the possible values of Q. So also in that case, we have no effect of the scattering cross-section for what concerns the temperature dependence of the process. And regarding the efficiency, in that case, let's say the cone at the angle at the center of the cone can be, let's say, can range from 0 up to a maximum value, but in that case, the angle at the center of the cone does not depend on the temperature, because the temperature just affects the number of phonons, not their wave vector, as in the high temperature limit, all the phonons are for sure active into the system. So due to that, we only needed to consider the contribution on temperature for what concerns the number of phonons. And in that case, that number scale with the, so we have this linear dependence here concerning the resistivity. There is only one, let's say, so for the moment, we know that the, we know, but we expect that the temperature, the resistivity dependence on temperature has always a polynomial structure, just proportional to t here and proportional to t to the power of 5 down here. But there is an exception to this dependence, and the exception may be best appreciated when we consider the low temperature regime, because a situation like the one that I'm going to draw here can be observed. So if we consider the same diagram, always the Fermi sphere first Brillouin zone for periodicity, we have another zone here. So if this is the first Brillouin zone, for the moment, I've always told you that given the initial state of the electron, in particular at low temperature, the final vector will be very close to the initial one. But in case the Fermi sphere on this side is very close to the Bragg plane, and for the same motivation, the Fermi sphere on this part is very close to the Bragg plane, then we have the opportunity to observe this kind of process. So if the Fermi surface is close so if the Fermi surface is close to the Bragg plane, then this means that with a wave vector q that is small due to the fact that, again, the Fermi surface is close to the border of the zone, so the distance between these 2 points may not be that large, there's the opportunity also in the low temperature limit to observe this jump of the electron from this point here to this point here. In this situation, we need to use the vector g, so to translate everything back into the first zone. So the consequence of that is that we need a vector g. So this is k prime. So we have that k prime is k plus q plus g. And an important feature that we have in this specific situation is that even if the change here in the wave vector of the electron, even if the variation of the wave vector is small, because in the low temperature limit, Q is expected to be small. So even if the deviation of the from this point to that point is negligible, then if we concentrate on the speed of the electron, here you have a speed that has this direction, but on this side the speed is nearly the opposite of that, because in this case we are on the right side of the Fermi surface. In this case we are on the left side of the Fermi surface, nearly on the opposite side. So if I now draw the velocity of the final state of the electron, I just draw that here to avoid confusion here, then we have something that is directed in this way. So this is the speed corresponding to level k. This is the speed corresponding to k prime. So in this case, the 1 minus cos theta contribution is not zero or close to zero, because even if Q is small, the capability of this kind of process to modify, to change the velocity of the electron is very, very large, it's quite pronounced. So in this case, the effectivity of the process does not scale with t to the power of 2. So here we have a strong contribution for what concerns the collision on the velocity of the electron, even if the exchange wave vector, if the modulus of the exchange wave vector is very low. And this kind of process is called, from the German term Umklapp, and Umklapp means in English fallback, so folding, kind of folding, or in Italian ripiegamento. So this term fold or ripiegare in Italian is due to the fact that here you have an electron that is moving, let's say, to the right, and here you have nearly an electron that is moving to the left. So you have kind of changed of nearly 180 degrees the direction of the speed of the electron. In this case, what is the temperature contribution that is coming from this kind of process? In this situation, there is a minimum energy that needs to be given to the system so that this kind of process may take place, because the minimum here you have a distance between this side of the Fermi sphere and this side of the Fermi sphere. So due to that, minimum distance means minimum value. So if we just plot one branch, Q and h bar omega, since we consider acoustic phonons, so the dependence is linear, if there is a Q minimum so that this process may happen, then there is also a minimum value for the energy. So at this point, the contribution of that process scales with the Bose-Einstein factor related to that kind of energy. So the number of phonons that, the number of processes that may take place due to that depends on the so that h bar omega minimum is fixed because that depends on the geometry here of the Fermi surfaces. So at that point, that is a fixed value. If the temperature decreases, then you have that this term here is the dominating one with respect to -1. So you have that at low temperature, this is the exponential of minus h bar omega divided by kBt. So the contribution of this kind of processes is exponentially depressed as the temperature decreases. So you have, for those processes, you have a temperature dependence that is more pronounced with respect to the T to the 5 law that was obtained before. And this is due to the fact that, again, you need a minimum energy so that that kind of process may appear in the system. So due to that, while the processes that were described up here may take place down to Q nearly equal to 0, in this situation, the minimum Q value is not 0, but is larger than that, and so the minimum energy. So due to that, again, you have an exponential depression of the contribution coming from this kind of processes with respect to the processes that came from the usual scattering. And just to, let's say, now use this term here to give a more general definition of the electron-phonon interaction processes, UNCLAP, apart from meaning folding or ripiegamento, is the representation of a situation where we need to use a vector belonging to the reciprocal lattice, so to fulfill the momentum conservation and to have the final momentum represented in the first Brillouin zone. So in general, UNCLAP process is a stage for a process where we need to use for the balance in the crystal momentum conservation a vector belonging to the reciprocal lattice. So UNCLAP is a term that in general defines processes where we need to include a vector belonging to the reciprocal lattice for so to fulfill the momentum conservation in the first Brillouin zone. Differently, all the other processes where G may be considered to be equal to 0 are called normal. So this is a representation of a possible normal process. So all the details were evaluated supposing that G is equal to 0. This is the representation of a possible UNCLAP process. That means a process where we need to consider the contribution of G, of the reciprocal lattice vector. Okay, and I would just like to, before adding a last comment concerning the contribution of phonons when we consider the dynamics of the electrons. Do you have questions or comments concerning this part? Okay. In this case, I just make a very short comment concerning the phonon. The phonon contribution in case we consider the electron photon interaction. If you remember, when we discussed about the electron-photon interaction, we said that we need to fulfill energy and momentum conservation. So we had that the energy of the final electron was equal to the energy of the initial electron plus or minus h times the frequency of the photon. So let's say in case we consider, let's say if we just focus on the absorption of the photon, then we have that the energy of the final electron is equal to the energy of the initial one plus the contribution of the energy of the external photon that is absorbed by the system. Regarding the crystal momentum, here we have the contribution of the momentum of the electron. Then we have the contribution that is due to the momentum of the photon. Then we have G. In that case, the let's say, I told you that since the wavelength of the if we consider this in the visible range, lambda ranges from 300 nanometers up to 700 nanometers. So 2 pi over lambda is smaller and smaller with respect to k. So in this situation, we may, let's say, neglect the contribution of the photon momentum. Due to that, we do not need G to fulfill this equation. So at the end, the final wave vector of the electron is nearly equal to the initial one. So in this kind of interaction, we have just the change of the energy of the electron, but the wave vector of the electron is always the initial one. So if we represent that on the, let's say, typical usual diagram, so if we use the nearly free electron approximation, we have that if the, let's say, if this is the initial wave vector for the electron, then the electron may jump, for instance, here, in case the energy of the photon is exactly equal to this difference in energy between this initial level for the electron and the final level. What happens now if we consider that this process takes place in a system where we have electrons, but we have also phonons there? So if we now include phonons, we have that the final energy of the electron, so if we add the phonons, the final energy for the electron is equal to the initial energy of the electron plus the energy of the photon, as we consider an absorption process. Then we have plus or minus the energy contribution that is due to the phonon, plus for absorption or minus for emission. We have also the crystal momentum conservation, so the final value for the electron is equal to the initial one. Then we have the contribution of the photon, then we have plus or minus h bar q, and then we have G. Since, let's say, E of k is in the electron volt range, H, the energy of a photon, is again in the electron volt range if we consider photons belonging to the visible range. The energy of the phonon is in the tens of milliV range. So as a rough approximation, we may suppose that this can be neglected, because that is very small with respect to the EV range where both the electron energy and the photon energy are found. If we consider the second equation, then here we may always neglect this term here. At this point, in principle, let's say we may not neglect h bar q because that is the crystal momentum contribution of a phonon. And in principle, we should not also neglect G because in principle, we may need that to fulfill the equation. But if just for a while, we suppose, just for simplicity, that we have G equal to 0, so normal processes, at this point, we have that if this is also 0, then we have that h bar k prime is equal to h bar k plus or minus h bar q. So in this diagram here, we need to consider also the contribution of the phonon when representing the final state for the electron. So the idea is that, for instance, let's say the change in energy will be always induced by the photon. So the vertical change is always due to the photon contribution, but the horizontal change is controlled by the phonon. So, for instance, also this final point here can be accessed if we just consider the energy requirement. So the final energy has to be over this line for this fixed value of the photon. So due to that, we need an additional change also in the horizontal direction to access this final point. So due to that, we may have a contribution. So the horizontal contribution can be given by the phonon, and the vertical contribution, again, is given by the photon. So in this configuration, we have that the final state of the system can be also accessed, let's say, the final state of the electron can be accessed by a contribution given just by both by the phonon and by the photon. So in this situation, the optical behavior of the system is more variable with respect to that it was accessed only in this situation where we consider only the contribution of the electron and the photon. So in this picture, considering also the phonon contribution, we have also the opportunity to access many different final points that were not accessible before, thanks to the, let's say, contribution that is given mainly on the horizontal axis, because on the vertical axis, the photon is the leading term, gives the leading contribution. So in this picture, again, there is also the opportunity to observe this kind of situations. So the final behavior of the solid is more versatile with respect to the behavior that can be accessed only considering the contribution of the interaction between electrons and photons. Okay, so this was just a short comment to say that apart from the resistivity, the fact that in the solid we have two systems, the electron system and the phonon system, may also change the behavior of the optical response to the system in the visible light range. Okay, as a, let's say, just to conclude this this part, I would like to let's say introduce the next part of the chapter devoted to phonons, and the next part is related to the capability to observe, more than to observe, to detect. So the idea is it possible to, let's say, find an evidence or find an experimental evidence that is in favor of the fact that, for instance, the frequency versus wave vector dependence has this structure, or in general to access the fact that there is a dispersion of the phonon frequencies with respect to the wave vector. For the moment, we have obtained, let's say, one result that is in favor of this dependence, let's say, that is in favor of the fact that here we have a nearly linear dependence of the frequency as a function of the wave vector, and that result is the specific heat dependence on temperature, because we have seen that the T to the power of 3 dependence of the specific heat at low temperature is related to the fact that the dependence of omega as a function of the frequency is linear in the low temperature regime. So somehow we have been able to say that, okay, in this regime, the relationship between omega and chi is linear. But let's say that is just a comment concerning the dependence. We have not the opportunity to let's say to verify these values and to verify also this part of the dependence. So the idea in this case is to exploit the fact that the phonons may interact with an external probe, and the idea is to, let's say, fix the parameters, the features of that external probe, let that probe interact with the phonon system, and then after the interaction, let's see, the idea is to see what happens to the probe itself and to detect what happened to the probe while the probe was into the system and interacted with the phonon system. So the experiment that one tries to reproduce is like this one here. So if this is your solid, you try to decide, and in a while I will tell you what is the process for this decision. So you choose one probe, one particle, you let the particle interact with the system, so you send that particle against the solid along this direction, and then you observe what happens. And for instance, if you observe a deviation with respect to the initial direction of your probe, a deviation that may be just on the direction of the of motion, so an elastic process, so the energy is always the same, but just the direction changes. Or you may also have a process where both the interaction and the energy may change into the system. So in this case, the idea is to exploit this change in energy and the change in the direction as a way to access what happened into the system and to obtain information concerning the phonons, because the idea is always to refer to the energy and momentum conservations and crystal momentum conservation laws in the system. So if we call E prime the energy of the probe after the interaction, we have that the energy of that is equal to the energy of the probe before the interaction, plus or minus h bar omega s of q, that is the contribution coming from phonons. Then we have also the second law, second conservation law, so the crystal momentum conservation, where for electrons and phonons, in this case phonons, we introduce the crystal momentum. For other particles, we introduce the full momentum. So we have the P for the, P prime, that is the momentum of the probe after the interaction, is equal to P, that is the momentum of the probe before the interaction takes place, plus or minus h bar q plus g, because we need to consider the additional contribution of the reciprocal lattice vector regarding the second equation. So the idea is to fix E and P, because you fix the initial state of the probe, then you measure E prime and P prime, so you know the final values of this. Let's say you know these values, you know these values, and you use this difference and this difference to access both the values of the energy of the phonon and the variation in the crystal momentum that corresponds to this variation in the energy. So this is, let's say, a general description that is fine for any possible arbitrary probe that you may send into the system and that may interact with the phonons. So the point is now, what is the best probe to say make this kind of so to observe this interaction. Now it's just let's say, I will not go on in this discussion because it's a bit long, so it's better for me to conclude that tomorrow morning. But what I just anticipate, what I will do, I will consider two kind of probes. One is photons, because we have just seen from the previous comment that we may expect the interaction between the photons and the phonons. Then another possible probe that may be sensitive to phonons is given by neutrons. Why neutrons? Because neutrons are not charged particles, so they have no interaction with the solid. Let's say in the solid we have a lot of charged particles. We have electrons and ions. So the fact that we use that we consider also neutrons that have no charge means that the interaction with the electrons, that are very light particles for what concerns their mass, can be completely neglected. So in this case, when the neutrons enter into the system, they have a strong interaction with the ions, because the neutrons have a mass that is larger and larger with respect to the mass of the electron. So again, the electron has nearly no effect during the motion of the neutron into the solid, but they will have a strong interaction with the nuclei. So in this case, they interact with the ions as the ions oscillate into the system. So we will check which of those probes will be the best one to observe this kind of interaction and to obtain informations, indications about the phonons features, and then we will see how is it possible to access both the change in momentum and the change in energy using the probe we will use for this kind of description. Okay, so it's better for me to stop now. So it's nearly 11:30. Okay. Yeah, stop the registration.